Your delusion. You gotta tell me if you're not taking longer geometry. Okay. We're just waiting for teachers. I think it's good. Too fast, too fast.
Anybody got questions concerning the quiz?
Well, no, that's the whole.
Chase have to go first.
Yeah.
I have to tell you something.
It's not 1A, 1B, yeah. There are. You do this first. You keep repeating. Wait, why should I T here? That should be nice. Saying so. That's why
He's not doing it. He's not doing He's very like, he's tied to the so he makes it more like
We can't work with them. I just thought that we were going to watch.
No, we are going to.
I thought there was like a set time.
Well, like you want to go, because how long is
I'm planning to get up in an hour, then watch the episode, and then watch it. But I can get no later. So what I just do is I do the minute and then eventually we just rewatch all the episodes. Okay. I think it just makes more sense. The show lost.
I've never had it.
I'm saying including even episode one. Like, so the show is lost on title. Do you remember it's like an hour and a half? I love it.
But I know he does like the upper.
I just, I watch episode I don't
It's really not.
Oh, because
This is such a struggle.
All right, I think it's time. Welcome back. I'm ready for the quiz. It's been there all along. That second one right there. Probably can't see it. Everybody ready? Here we go. I hope you can see the exponents there. The first one says give a grammar for that language. It says A, B, A to the N, B to the N, A to the K. And then the other one, find L of G for this grammar. And you can write it as a set or describe it in words if you prefer. let's have a couple more minutes. About time to send them in. All right, I think everybody's done. Let's chat about it. By the way, I just saw a news alert. They're going to renumber the exits on the Merritt Parkway. Can you believe it? It's the kind of thing that the Google News sends to me because they think I'll be interested. I am kind of, I guess. So the first one there looks to me like a concatenation of things. There's kind of the A, B, the A to the N, B to the N, and the A to the K. This is one way to think about it. There's different ways you could think through this, of course. But if you think of it as concatenation, then I would say something like, you know, S goes to, the first thing, actually the first part is always AB. So would you mind if I just put AB literally there, and then maybe I'll do a S1, S2, where the S1 is going to become the A to the N, B to the N part, and the S2 is going to become the A to the K. And those are all things that we've seen before, so I hope you remembered. To get A to the N, B to the N, it would be like this, A, S1, B, or epsilon. And to get A to the K, I would just do S2 goes to A, S2, or epsilon. So that's how I did it. I hope you did something like that. There are many other ways you could have written the same basic idea. If you were thinking of it as a concatenation, you might have done something like S1, S2, S3 here, and then say S1 goes to AB, and then the other ones like I did. So, and that's fine. All right, great. And the other one, find the language of this grammar. So that means you should tell me the set of all the strings that this grammar can generate. And when I look at this, so this, I suppose you could say, is kind of like a union. The S either becomes that or it becomes that. And the one on the left there I would think of as this is a string which begins and ends with an A. This one over here is a string which begins and ends with a B. And then what can the T turn into? What were your thoughts about that? What if you do this T, what kind of strings can you make with the T? Anybody feel good about this one? Yeah?
A bunch of A's and B's.
Yeah, the T actually can become anything. With A's and B's in any order you want, right? By doing this step over and over again. So how I would describe this in words, it's any string which either starts and ends with A and has whatever you want in between, or starts and ends with B and has whatever you want in between. That's how I would have said the answer to this. If you want, you could have written this as a set. I mean, I don't know. It's something like AXA, where X is in AB star. Union BXB, if you really want to write it as a set, it's something like that. Although I don't think that's, I think what I said in words is clearer than that. You could write this as a regular expression, I guess, if you want. A plus B star A, or B, A plus B star B. Although, again, I don't know if that's a very clear way of writing it, but it's correct, yeah.
Put extra stars in the A's and B's in the parentheses. Does that also work?
Extra stars, like here and here? Yeah, it ain't wrong. The extra stars are not necessary, but that's okay. Yeah. Any other? What if I said we could do this all day? Yeah. All right, great. I hope you said something like one of those. Okay, let's talk some more about stack machines. That's what we're doing today. Yes?
For some reason, it's not letting me even select the PDF to upload. Can I email it to you?
Yeah, sure. Yeah. No problem. Yeah, let's talk some more about stack machines. I want to do a bunch more examples today and maybe talk about some sort of theoretical aspects, but I think mostly examples. We are trying to get a feel for creating a stack machine to do, this or that, and also the general question, as usual, is like, what kinds of languages can you create using stack machines, and how does that relate to regular languages, NFA, DFA, or languages which can come from grammars, context-free grammars. Those are all the questions that we are discussing related to stack machines. I thought we should talk about one example, which is kind of like a classic example of a stack machine. I want to talk about a stack machine for balanced brackets. This, of course, is a very important thing in real-world programming, just like balancing your parentheses properly. If they're not balanced, then you get some kind of syntax error or something. This is meant to be a stack machine which reads a string and tells you if the parentheses are balanced properly or not. So, and I'm going to consider just a language which only has brackets in it. It doesn't have other stuff. But if you wanted to, say, look at an ordinary piece of Python code or something, first throw away everything except for the parentheses, and then you do what we're talking about here. So a stack machine for balanced brackets. We want strings to be accepted if they are properly balanced, right? If they are balanced properly. And like I said, I'm just going to think about the sigma here. My alphabet is just that and that. This looks weird, but what I'm trying to say is the alphabet letters themselves are these two bracket symbols. All right. So this is a string is just going to be a bunch of brackets, left brackets and right brackets in some kind of arrangement. So for example, this one is accepted, I think. This is not terribly easy even for a human to do, but are these brackets actually balanced properly? If I were doing this as a human being, which I am, I would do something like, okay, these ones go together, and then these ones go together, and those ones go together, so that one goes together, so that one. Okay, so it is properly balanced, all right? I will point out, though, it's not at all clear how you're supposed to do that. If your job is to do this by hand, you will notice that as I was checking these brackets, I sort of went left to right here as I was looking, but I saw this guy and matched this guy, so okay, that's fine. But as I'm going left to right, when you see this bracket, how do you know where the matching bracket for that one is? The answer is it's kind of complicated. I just kept on going and matched some other thing, and then matched some other thing, and then, okay, then I realized that this one actually matched that one over here. But it's not, to me at least, it's not very clear exactly how that's supposed to work. If you ask me, for instance, to write a Python program to decide if that is properly balanced or not, I would say, I mean, I could probably do it if you gave me some time, but it's not exactly obvious to me what the proper strategy is to do that. But anyway, this stack machine is going to do this for us. So that should be accepted. What should not be accepted? Obviously, you know, something like this is rejected, right? Or something like this, that's rejected. I mean, that one has too many left brackets, but not enough right brackets. But this one here, interestingly, it does have the proper number of left and right brackets. It's just they're not in the right places. So whatever this machine does, it's not just going to be about counting how many of each there are, because it's more complicated than that, right? Or something like, how about, I made up another cute example. This is another example in which I believe there are the correct number of all of them, but they don't properly balance. They balance kind of like that. Maybe there aren't the proper number. It looks like I have an extra right-hand side. All right. But anyway, it's not, what I'm trying to say, on some kind of basic intuitive level, this is actually not an easy question to answer. At least it's not sort of immediately obvious if they're balanced or not. All right. Actually, you can do this quite easily using a grammar. It turns out, and this is kind of complicated, and so it's not, perhaps not immediately obvious that this is correct, but it turns out that this is actually a grammar that gets you all possible balanced bracket strings. So it's kind of cute. You have to create the two brackets together so that you guarantee that they're always balanced with each other. And then if you want to put more stuff inside, then that's why there's another S on the inside. If you want to put more stuff next to it, that's why there's an S here. And it turns out this is grammar for the whole thing. But anyway, I want to do this as a stack machine. So this can be done with actually a very simple stack machine. I've heard it said that this is like the classic case of a thing that is good to do with a stack machine. This can be done with a very simple stack machine. And I will try to give you sort of the idea here. The idea is we read one of these strings, maybe this one I'll copy down here. Read the string, let's say left to right, because that's, I mean, this is how a stack machine has to work. It reads the string one character at a time, left to right. And when you see a left bracket, if we see that thing, then put, I meant put, not but, sorry. Put, let's say, a big X on the stack. So every time you see an opening bracket, I'm going to put something, maybe I should say push. Remember, that's the technical word that we use for putting something on the stack. When you see the left bracket, you push an X onto the stack. And if I see a right bracket, so the stack is kind of representing how many opening brackets have I seen so far. And every time you see a closed bracket, you should throw away one of those things from the stack, because the closed one is supposed to match an opening one. All right, so if we see the left bracket, put an X on the stack. If we see the right bracket, pop the X from the stack. And that's really all that it takes. If the brackets are properly balanced, then every right bracket will match a left bracket that you've already seen before, and so you can pop it off from the stack. And if they really are balanced, then all the x's that you push onto the stack will end up getting popped off by the end, and you'll end up with an empty stack. So this will work out perfectly. Let's see if we can just write the stack machine formulas. So I hope you remember from last time. Every stack machine looks like these sort of rules. Read, pop, push. All right. And you'll notice my description of the stack machine. Actually, I didn't mention the stack symbol S, which in this stack machine, you can sort of do this whole thing without using S at all. So I'm going to put one sort of dummy rule. Read epsilon, pop S, push epsilon. This will allow you to just get rid of the S, because in my strategy here for using this stack machine, the S is pretty much totally irrelevant. So this will just get rid of the S. That's kind of a technicality. But the real steps in this is I have a read left bracket, pop epsilon, push X. So that means if you see a left bracket, you don't pop anything. That is to say, you leave the stack like it is. Well, you don't remove anything from the stack, but instead you push a new X onto the stack. Right? And the other one is, what do I do if I read the other guy? Can anybody translate my language into the stack machine framework here? Read the right bracket. Yeah? Pop X, push epsilon. Yeah, great. This is kind of the simplest stack machine I can imagine for an alphabet with two different symbols in it, right? Yes?
Is it okay if this accepts nothing? Because like if it gets rid of the S, it stops there.
Yes, you mean it accepts the empty string?
Yeah.
Yeah. Well, yes. To me, if you ask me, is the empty string properly balanced in its brackets? I would say, yeah, sure. Why not? There's no brackets, and so yeah, let's say that it is balanced. Yep. If you don't want the empty string, if you want to accept all balanced bracket strings except the empty string, then I'm actually not sure how you would do that. You could add some other rule to make sure it's not empty, but that would probably mess up what we have so far. So I don't want to think about that. Well, it is possible, but it would be slightly a pain to do. Can we just sort of try and convince ourselves that this actually works properly? So let's try to do this particular string here. See if we can make a stack derivation for showing that that string there is accepted. So I'm going to, maybe I'll label my steps here, 1, 2, 3. We're not always going to label the steps in these examples, but since we're just getting started here. So I hope you remember, when you are doing a stack machine derivation, we begin with the string, comma, S. The string that we're trying to test if it's accepted or not, comma, S. And then we do the appropriate steps. So since I have an S on the stack, actually this, you can do rule number 1 now, or you could do it at the very end. We might as well just do it right now. So I'm going to do rule number 1. This is read epsilon, pop S, push epsilon. That means the string which I'm reading does not change, because this is a read epsilon step, but the S goes away. All right. Okay. Next, let's do step 2, read left bracket. What if the string began with a right bracket? Actually, if it began with a right bracket, the only step you're allowed to do is pop X, but we don't have X here, so we would be stuck at that point. But actually, this is appropriate, because if the string begins with a right bracket, then it's automatically not balanced, and so it should automatically be rejected. So that should feel good. Anyway, let's do rule number 2 first. So I'm going to read the left bracket. That means this time I write this string here, but without its first left bracket here. So it's just this much. I hope that's what you said. Remember what you see in these pairs? These pairs are called IDs, instantaneous descriptions of the stack machine. This thing here is the portion of the string which I have not yet read, and then on the right side of the comma is the stack. Okay, so I read the left bracket, and that's why it doesn't appear here anymore, and I have an X on the stack. Next, I'm going to do rule number 2 again, because it's another left bracket. Really, there's only one way this can go. And now the stack says XX. All right. Now I see a right bracket. We don't have any kind of opportunity to make our own choices here, really, in this particular example. I'm going to do rule number 3 to handle the right bracket. This is a pop X, and so one of those X's should go away. So it looks like that. Next, I'm going to do a step number 2 to read the left bracket there. So it says left, right, 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 and now X, X. I hope I'm doing okay here. You can show your friends your notes for this one. It looks crazy. Next is a left bracket, which is again rule number 2. Okay, now it says right, 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 X, X, X. And now I'm going to do rule number 3 3 times, and I end up with empty string, which is what we're looking for. So I go bracket, bracket, X, X, do it again, 1 bracket, 1 X, do it again, epsilon, epsilon, check. Epsilon, epsilon is what you want to see. Yes?
Is there a way we could speed up the steps by doing the same rule multiple times, like in one go?
Yeah, you mean a way to write that?
Yeah.
Yeah. So in our book, they use sometimes like that, this here, I did arrow 3 times. You might see them write something like arrow 3 star, meaning I repeat arrow 3 0 or more times, I guess. Yeah. I mean, this is just writing, like if you were doing this on a homework problem or something, certainly in this example, once you're doing this, it's obvious to me. If you put some like dot, dot, dot or something, that would be fine with me. If it was really obvious. I think this particular example is so simple that it's pretty straightforward. All right, can we just try one that's not accepted? So something like this, right? That one should be rejected. Again, we can begin with that rule number 1, the one that just throws away the S. Although you could do it at the end if you want to. It doesn't really matter, but I would start off with those brackets followed by the epsilon, and then I have to read the left bracket, which makes it into this. Then I could read the right bracket and pop the X. But here we are stuck. And so that string is rejected. All right, I didn't label my little steps here. That's a 2, that's a 3. All right, I just want to make sure everybody remembers how the stack machine works. If you get down to epsilon, comma, epsilon, then the string is accepted. If that is not possible to reach epsilon, comma, epsilon, then it's rejected. All right, this is the classic stack machine for balanced brackets. All right, anybody got questions or thoughts about that one? I have one that's kind of a variation on this. In this example, we use the stack to kind of remember how many left brackets we've seen before, or like how deep are we into the opening brackets. The number of X's represents that thing which you are remembering from step to step. And that's really the only thing you have to remember. Let's try, I got a slightly complicated, but it's this is still a variation on the one that we just did. So let's say this is X in AB star, where the number of A's equals the number of B's. All right, the number of A's equals the number of B's. So my strategy here is, if you do have a string which obeys this property, it would look something like that, right? Here I have 4 A's and 4 B's each time. What I'm going to do is think about this in terms of, I would say, imagine A's matched with B's. And so as I read the string from left to right, I'm going to remember, sort of in quotes, just like remembering like a stack, how many extra A's have I seen so far? And I'm going to say, if we see extra A's, I want to push X onto the stack. All right. This is just like in the previous example, the stack keep track of how many extra left brackets you saw, and then every time you see a right bracket, you cancel off one of the X's out of the stack. This is the idea that I'm going to try and do here, only the X this time will represent extra A's that I see in the string. And so every time you see a B, you should get rid of one of those X's, because I imagine each B is supposed to match with one of the A's. So if we see extra A's, push X, and then when we see B's, you should pop X. All right, just like matching the left brackets with the right brackets, I'm matching A's with B's, because my goal is that the number of A's should be the same as the number of B's. All right. As I've described it so far, this sounds exactly the same as the previous example. The difference, though, is in this case, you might at some point see extra B's, right? And then what am I going to do on the stack to indicate extra B's? You can't throw away an X that doesn't exist there. So I'm going to use another symbol. So I'll say if we see extra B's, I'll push a Y, say. Because sometimes you might see, as you're going left to right through the string, you might have extra A's at the beginning. You might also have extra B's at the beginning. We need some way to indicate that. So if we see extra B's, we push a Y, and then in that case, when we see A's, you pop the Y to sort of cancel off the fact that there were extra B's, and you are matching them up with A's. All right. So this is similar to the previous example, but there's kind of an extra thing that we have to keep track of. In the old example, you want to reject it automatically if there's extra right brackets with no left brackets, but not the case here. All right. Anyway, can we try to write this into a stack type machine? In this case, I'm going to make it so that we don't throw away the S right at the beginning. I want to imagine that we sort of keep the S around until the end. So I'll just say let's keep the S. Although you might be able to rework this to throw away the S at the beginning. But anyway, I'm going to do read, pop, push as always. And the idea here, let's imagine, first of all, there are some cases when S is on the stack, which is like you can imagine, this is what should happen if we're just starting off and the very first thing you see is A. So that's this situation. If S is on the stack and the very first thing that you see is A, then what should we put on the stack? Now I said, when we see an extra A, which this A is extra because it's the very first thing we're seeing, then I want to push X, all right? So this, actually, the way we have to do this is like that. I don't want the S to disappear forever, so I push XS. That is, there used to be an S on top of the stack, now there's X and S on the top, all right? So that's when I see A as the very first thing. What about if the very first thing I see is B? Well, that means that B is, that means I'm beginning with sort of one extra B. So that one should look like this, right? BS and YS. And then we just need rules that describe what happens if there's an S on the stack. So basically I'm going to fill in rules like this. BX, not C, come on now. AY, because there could be an X on the top of the stack when you're reading an A, or there could be a y on the top of the stack when you're reading A, and then similarly for B's. All right? We just have to decide for each of these things. Anybody want to say, what if there's an X on the stack and I read an A? What should happen to the stack in that case? Anybody got ideas? The idea here is whenever you see extra A's, you push an X onto the stack. Now, if there's already an X on the stack, that means we've already seen some extra A's so far. I would say this means we should put another X onto the stack, right? If you already have extra A's and you see another A, then that means I got one more extra A's. So here, I'm going to put XX, meaning there used to be one X on the stack. I am going to add another X onto the pile, but since I popped X, I have to put back two X's. Right? Yes?
What about the S?
So the S presumably is buried underneath this somewhere in the stack. The S is probably lower down. Remember, these lines, this pop line only refers to what is exactly on top of the stack. So the full stack at this point might look something like X, 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 and the S is on the bottom. And what this rule says is, if there's an X on the top, throw this X away, but replace it with two more X's, which results in one more X being added onto the pile. All right, great. What about B and X? Read B, pop X. What should happen here? That is, if you're reading a B and there's an X on the top of the stack. I think I said. When we see B's, pop X. That is to say, if you see a B and there's an X on the top, you should just get rid of that X. And so I don't want to replace it with anything here. I'm going to put a push epsilon. That X should be thrown away because the idea is a B should cancel out an X. And A should make an additional new X, all right? And then for the Y's, it goes sort of the other way around. An A is supposed to cancel out a Y. So it's going to say read A, pop Y, push epsilon. And a B, the Y is supposed to represent extra B. So if you see a B with a Y, that means we want to make an extra Y like that. These are all the basic steps for this stack machine. And if you do all this stuff properly, you will be able to sort of cancel out all of the X's and Y's appropriately. You will be left with just S at the bottom when you get to the very end. And just to finish it off, we need a rule like this, epsilon, S epsilon. So this rule is meant to only happen at the end. Clear the S away. Come on now. All right. That rule we're only going to do as the very last step. Yeah?
Is there a reason we do that at the end, not the beginning?
I would say not really. I mean, the way that this is written, you can tell in these rules that you're intended to, at the very beginning, do one of these two rules rather than throw away the S entirely. Yeah. If you don't see it, if you don't do this, if you do clear the S at the beginning, then you actually won't have anywhere to start because these other rules, they require either pop X or pop Y. And if you start with nothing on the stack, then you can't do either of those rules. So you could probably change this around to make the S pop at the beginning, but you'd have to rewrite the whole thing, basically. All right. Okay, can we try some, test out, is this string accepted or what? So how about let's try A, B, A, B. This one should be rejected, right? Let's just see if we can do it. So I'm going to start with A, B, comma, S. I didn't label my, my steps here, but that's kind of how we're usually going to do this. I hope that you're comfortable enough with the stack derivation to be able to tell which rule is being used at which point. The only rule we could do, well, you could do the very last rule here, then you would immediately be stuck. So let's not even try that. We should try the top rule, right? Read A, push S, read A pop S, then I lose one of my A's on the left side of the string, and then instead of the stack saying S, it now says XS, right? That was a pop S, push XS. And then I have another read A, pop X. So now it's going to say BAB, XXS, right? XXS, not my t-shirt size. All right, let's continue. Read the B. Now I have a read B, and it better be pop X, because I have X on the top of the stack. So that will sort of kill one of those X's. Now it says AB, XS, right? And now I have a read A pop X, which gives another X. So I have B, XXS. I hope I'm doing okay here. Now I have read B pop X, push epsilon. So this says epsilon XS. And now we are stuck. And so this string is rejected, because actually there was no other choices that I could have made along the way here, except for just popping this at the very beginning, which also would have made me stuck. All right, so that one is rejected. Would you mind, I have one for you to try. Just see if this string is accepted or rejected. See if you can write the derivation. If you know what's going on, this is always going to be pretty easy to do. First of all, just by looking at it, I can tell this should be accepted, right? Because it has 4 A's and 4 B's. So see if you can write down the proper derivation, which makes that accepted on the stack machine. Maybe I'll do it myself very slowly here. Don't look if you don't want spoilers. Yes. This is read A. So do white A's here. Yeah, after you read it, you don't write that letter and give whatever data. Oops.
Yeah, how do I know which because it based on which ones are to me. Maybe you just know.
Which step to use?
Yeah.
Yeah, so this is, so you have to read these. There's an X on the stack, so the to-do has to be next. Okay.
All right, I'm going to write the rest of my answer. I hope everybody agrees with what I've got so far. Sorry, that's not what I just wrote. It's not right. I read a B with a Y, gives me an extra Y, like so, right? B-A-A-Y-S. A-A-Y-Y-S. The big X's represent A's, the big Y's represent B's, and an A cancels with a B. This is how you think of this, this stack machine is how it works. And A's cancel Y's, so this goes to A-Y-S, and then empty string, comma S, and then using the last rule there, or the first rule, I don't remember the last one, you can throw away the S. I hope that's what you said. I mean, as I was going around, this is fairly straightforward. You just have to think it through and work it out. All right. So the idea of a stack machine is it's kind of like maybe a very stupid computer which has just one sort of thing that it can remember at a time. And in order to balance brackets, all you need to remember is kind of how many left brackets deep am I, and in order to match up A's versus B's, you just have to remember how many extra A's have I seen, or how many extra B's have I seen. So that's how it goes. All right. Let's talk a little bit about the relationship between the languages you can get here versus other types of languages. And I want to talk about regular languages. So how about, the big question is, can we do any regular language on a stack machine? All right, that's the question, really. And if so, is there a nice way to, for instance, if the answer to this is yes, it means you could convert any NFA into a stack machine, or you could think of it as convert any regular expression into a stack machine. So here I will just as an example, let's just write a little NFA over here. And I'll give names to the states just so that we can talk about them. I put an epsilon transition in there just to make it interesting. All right, so this NFA here, can we convert this to a stack machine? Remember, a stack machine is capable of kind of remembering one thing at a time, right? Is it possible to convert this to a stack machine? Let's, for example, if I could ask, as we always do for NFAs, I could ask something like, is AABA accepted? And what it takes to answer that question is, if I were doing this myself, like as me, as a human being, I sort of put my finger here in the starting state, and then I imagine reading one letter at a time and moving my finger through the diagram as I go, right? If you like, I am kind of using my finger to remember one thing at a time, and that is just as you read the string, you keep track of what state you're in, right? You can do that fairly easily with your finger, but I feel like you could also do that with a stack machine. A stack machine can remember one thing at a time, and the stack machine should be able to remember which of these states the thing is in as you read one letter at a time. So this is the idea here. Our stack machine can keep track of which state we're in. On the stack, right? And conveniently, I labeled the starting state as S. So when you begin, the stack says S, right? And then what if you read a when the stack says S? Well, that means you should probably make the stack say T, because you can go across to T in the NFA. Now the NFA also can go down to Q, so that means the stack machine will have two different rules. One which can read A and go over to T, but then there should be another one which can read A and go down to Q. All right. So these arrows on the diagram can directly translate into stack machine rules. So I'm going to go read, pop, push. So if I read A with an S on the stack, I should push Q. Or if I read A with an S on the stack, I should push T. I don't know if you ever wondered, am I allowed to put two separate rules for the same read and pop? And the answer is yes. So the stack machine can have, you would say, sort of non-deterministic rules. That is to say, two separate rules which you are allowed to do either one, and it's kind of up to you to choose the correct one. But these two rules indicate the fact that if you're in state S and you read A, you should switch to either state Q or to state T. All right, and then every arrow here can just be translated into a new rule for the stack machine. So for instance, can somebody say maybe what is this, how would I write this B arrow here, this diagonal one? Yeah?
Read B, pop T, push Q.
Yeah, great. Read B, pop T, push Q. That means if I'm in state T and I see B, we should switch it to state Q. Next I have an epsilon arrow across the bottom. That's a read epsilon. The fact that it's an epsilon really doesn't matter at all. That's a read epsilon, pop Q, push R. And then I have the arrow R, sorry it's hard to see at this point, R going up with an A to T. That's a read A, pop R, push T. All right? And that's pretty much it, although this is not entirely it. Can anybody say this is missing something which we haven't sort of described yet? Yeah.
Should you have read epsilon, pop or pop R, and then push epsilon?
He said, I like this idea. Read epsilon, pop R, push epsilon. Why is that?
Because it's the accepting state.
Yeah, so this here indicates that R is accepting. So if somehow you got to a point where the stack has R in it and there's nothing else, then you should be able to pop the R and end up with empty stack, and then your string will be accepted. Yeah, great. So in this case, to accept, now one thing that's a little tricky about this stack machine is, like I said, there are some steps which are kind of up to you to decide which one to use. Like there are two steps for read A, pop S. So if I give you a string, how can you tell which of those is the appropriate one to use? I will say to accept a string on this, you have to be proper about what precise sequence of steps you're going to use. And I would say my advice about this is to accept a string, do the same steps as you would on the NFA. All right, so for example, maybe I'll copy this down so I don't have to scroll it. So if we can see everything at once here. Let's do the, let's derive A, B. That should be accepted, right, on the NFA? Because on the NFA, I started state S, I go A, B, and then epsilon, right? Across to T, down to Q, and then the epsilon. So those are, I'm going to try and do those three steps in that same order. So derive A, B on the NFA. It's like this sort of Z-shaped those arrows are what we're doing in that order, right? And so I'm going to do, on the stack machine, do that same exact thing. So I start with A, B, comma, S, of course. And then which of the two rules do I do first? Is it the pop S push Q or the pop S push T? I just said I'm trying to mimic these three steps on the NFA, which means I should do the T one first. So I go pop S push T gives me B, comma, T, right? And next I want to do the diagonal arrow, which is a read B, pop T, push Q. So I'm at epsilon, comma, Q now. And next I do the arrow across the bottom on the NFA, which is that epsilon arrow, which has the epsilon arrow, read epsilon, pop Q, push R. So this becomes epsilon, comma, R. And then R is the accepting state, and so we do that very final stack machine rule to make it epsilon, comma, epsilon. So we are just trying to mimic the NFA steps by doing those same stack steps in the same order, all right? And this is always going to work. If you have an NFA, you can directly translate it into a stack machine like that, all right? So what that means, if you would like to, if you want to write this sort of as a theorem about regular languages and stack machines, it means if L is a regular language, if L is regular, then there exists a stack machine, I'll call it M, with L equals the language of M, all right? So what I'm saying is every regular language has a stack machine that makes that language. And how would you find that stack machine? You make an NFA first because it's a regular language, and then you can convert it to the stack machine in a very simple way. All right. And maybe I'll just say the precise steps. I didn't say this very clearly, but I hope it was. I mean, this is not hard, so I hope that this is fairly clear. But I will sort of label this. This is probably something you'll end up forgetting before our next test, but this is, I guess our next test is, in a week and a half, right? Not next week. The next time, because it's Easter. To convert NFA to stack machine. This is something you will want to remember how to do. It's not hard, you just have to remember the process. So any arrow, the arrows that go, if you had an arrow that was something like this, between two states, this becomes read A, pop X, push Y. Right? And if you can remember that, that's basically the whole thing. Right? You just translate each arrow directly into a line like that. If you had an arrow looped back, like X going back to itself, then it would be read A, pop X, push X. Right? That's easy enough. And then you also have to remember the accepting state. So something like X being an accepting state gives you a line that says epsilon X epsilon. Right? That means you can clear off the stack to nothing if you end up in one of those accepting states. All right. How about you try one? Can I get you to try one? So your job, convert this to a stack machine. Provided you know what you're doing, this is not hard to do. Convert this to a stack machine and show a derivation of A, B, A, B. Here's the NFA that I'm talking about. This would be a nice leisurely test question, I would say, because it might take you a few moments to do it, but you don't really have to think too hard. You just have to remember how to do it. A nice relaxing test question. See what you think. Feel free to chat with your friends.
Is that from the loop?
Yeah, it should say yes. It's like any of the other arrows, it's just the endpoint happens to be the same as. All right. Looks like folks did pretty good here. Can we chat about that? So, first of all, I'll make my machine here. It involves just translating one by one all of the arrows. The very first one I see there is S going back to S with a B. So that's, you know, this is the instructions. Oh, sorry. In general, you do this kind of a thing. If you have a looped edge like this, you should do it just like this, only you sort of imagine that the Y and the X are the same. But in this case, I would say read B, pop S, push S, right? BSS. Good thing that was a B and not an A, am I right? That would have been a bad word. S going to X. This should say ASX. Once you know what you're doing, there's not a lot to this. The looped edge on X should say BXX. The vertical A from x to y should say A, x, y. The loop B on y should be B, y, y. And the A from y to s should be A, y, s. And then because s is an accepting state, I need a epsilon, s, epsilon. And I think that's it, though. I hope everybody agrees with my rules. Okay, and then can I do a derivation of that string here, A, B, A, A, B? So I begin with A, B, A, A, B, comma, s. All right. Let's see, on my thing here, you want to do whatever step is appropriate to follow the arrows. Although in this example, maybe there isn't much that could go wrong here. But I'm in state S and I read A, so I'm going to do ASX here. So it becomes BAAB, comma, X, right? I throw away the S and make it an X. Now I have a B and an X. The only one I can do is this line. Read B, pop X, push X. So this becomes AAB, comma, X. Then I read A, pop X, push Y. That's the only appropriate rule at this point. So that's going to say AB, comma, Y. Now I do read A, pop Y, push S. That is B, comma, S. And then I do the BSS line, gives me epsilon S. And then I do the final thing, gives me epsilon, epsilon. Ha-hey, and I feel good about epsilon, epsilon. There's something kind of satisfying about finishing with the epsilon, comma, epsilon. I don't know if you feel it too. All right. We have 5 more minutes. I think this will do us for today, though. The next thing I want to talk about is doing a similar thing for grammars. Can we convert back and forth grammars and stack machines? That is quite a bit more complicated, so let's leave it to next time. I'll see you all then. Hope you have a good weekend.